Okay, so the topic of this week is going to be an introduction to automation, which is going to take us into the final project for the rest of the semester. So what this is today is going to be a follow-up to the lab that we started on Monday and Wednesday. Basically just gave you one image of the different kinds of digital fabrication that we're going to be exploring with our scripts. And I wanted to expand on that today so you guys have a sense of the role that automation plays in digital fabrication. But before I do that, I want to take a step back and I want to talk about what automation is. And I think we all kind of have maybe a sense of that. I think there are a lot of things in our lives, right, that we know that are like automated. Have things like washing machines. We have like algorithms that set the street lights. We have algorithms that like set the that like manipulate the stock market. Okay. But this all goes back to, even things like agricultural tools, right? And they're not exactly a form of automation, but they're definitely a form of like mechanization of saving time and labor, saving us like energy, right? So instead of like plowing the fields by hand, we would have like a mechanical plow, right? Or a mechanical planter, or like a mechanical tiller. Okay, I'm from the Midwest, so I know a lot of farm equipment. So the very idea of it begins with this thought that you could do it yourself, but it would take you a very long time, and you might not have the power or the like strength or the accuracy to do it over a long time. Okay, and then we get into things like industrialization, right, where we begin to get like windmills and coal-fired power plants and steam power, and we're able to create things like mechanical lathes and industrial presses. And so again, we're like magnifying the power that we have. We're increasing the accuracy of the actions that we take, right? So now we have all of the parts for our rifles are actually made the same, and every single rifle we make is the same. We have like the cotton gin. All these kind of inventions, right, that sort of come about in the 19th century that allow us to begin to increase our productivity and increase our production. And we get into the early 20th century with computation, right? We get into World War II. We're looking at our goal of automation as it's been since the time of Newton, where we can automate logical processes. So we have machines that if they don't think, they at least help us to think in abstract ways. So the introduction of the computer was originally for, basically trying to break, the enemy's codes, which is something that you could do, but if you had an infinite amount of time and patience, and the war was on, we don't have that, right? So we got to crack these codes right away. So they invent the Enigma machine. Sorry, not the Enigma machine. The Enigma was that they're trying to crack. They invent a computer to crack Enigma. And then we get things like trying to tie mechanical precision and logic with physical activity. We get things like the bomb sight. We get things like anti-aircraft gun control systems that are actually using logical processes and physical processes like together to automate tasks. Okay, and that brings us to where we are today, where we have computers in everything. And once you have a computer that's programmable, you can program the program. Okay, and that's what scripting actually is. If we begin to think about it, we're very careful in architecture not to call it like programming. I think we don't want to like convince ourselves that we're actually writing programs, so we call it scripting. And if we want to get really like sort of like semantic about it, scripting is writing a program that's on top of another program. Okay, so we're automating like other tools, and that's what Grasshopper does, right? It automates Rhinoceros. Okay, and digital fabrication, which is the kind of moment that we're at in architecture right now, is this idea that you could fabricate these things by hand, right? You could get a jigsaw, you could get an X-Acto knife, I don't know, you could get a laser in your hand, right? And if you really like wanted to, you could actually cut that stuff out. But it's much easier to have a machine that's numerically controlled, that's programmable, right? That you can program. And the tools that we have, like we have the capability of like drawing in the computer, of modeling in the computer. Those can talk to the machines, and those machines are going to do the fabrication. Okay. The last piece of it, the last leg of it, is the fact that like at this point, for the most part, even when the stuff gets fabricated, you've got piles of the stuff that's laid out. Somebody still has to actually put the stuff together. Okay. And so a lot of automation that we're doing at the moment is about actually coordinating those efforts. Things as mundane as labeling and like drawing diagrams of things, right? Which again, you could do by hand. It's much easier to make a tool to do that for, okay? The last part of the day I'm going to talk about, though, is the future, which is that we are going to have automated construction. Okay, and some of you guys may have seen some of this. If you haven't, I've got some visual treats for you. We're experimenting with robots and self-assembly. So we've got things now we can fabricate the parts, and now the parts can fabricate themselves, basically. Okay, so that's all exciting territory. I'm about to take it a little bit more mundane. Okay, so I'm gonna go through the 3 different types of fabrication and the different kinds of like automation that are involved, and it's a precursor to the work that you guys are gonna do for your final project. All right. So this is an example of what's kind of involved. This is a cut sheet for a project. Each of these is like a 4x8 sheet of material. You can say plywood or steel or whatever. And these have been plasma cut or they would be CNC milled out of these sheets. This is a pretty impressive effort, right? The sheer amount of pieces, the precision of the cuts in the pieces. Something's really going on here. There's a lot of little like fine pieces in that sheet. The nesting of the parts. So nesting is this idea that you're trying to optimize so you have as little waste as possible on that sheet. We could cut one of these out of a sheet of wood, but that would be terribly wasteful. And so there's actually algorithms that will actually optimize, actually there's that word again, optimization, that'll optimize the pieces to fit with the least amount of waste possible. Okay? But the very process of taking a model that you guys may have made in studio, right, that I think we've been able to do, taking it, cutting it into something that's flat, which is actually interesting too, because a lot of the materials that we have are flat, but the stuff we're trying to make is not flat. So figuring out a way to break it down into sections or break it into facets, cut notches in it so that you can fasten them together, right? Drill holes in it, cut plates into it, and then distribute it onto these sheets is really what I'm talking about today, is this task of automation. So you guys have gone like, halfway down the football field, right, in terms of like actually making some objects and even optimizing those objects. But the last half of the field is actually getting this stuff out into like the real world, okay? And again, some of this might be territory that we've talked about. You may have talked about it, I think in second year, certainly. You may have seen some of this. But I want to cover it today in terms of the computational methods involved. But this is where we're headed. So the first technique I want to talk about is sectioning, and I actually call it contouring, I suppose. It's basically this idea of you have a three-dimensional form, and you're going to cut a series of linear sections in one axis. And typically that's an X, Y, Z axis, but it doesn't have to be, right? Depending upon the object, you can bring in a vector from any angle, and you can begin to cut sections of that. When you're designing your objects, you guys have made these things, or you're making them over the weekend. When you get to the next part of fabrication, don't necessarily go with your gut to just like fab it like one way or the other. Really experiment with the like grasshopper. This is the ability you have with it to decide like what's the effect that I'm going to get when I cut a section from some other angle, right? What if I do it sideways as opposed to like straight up and down? Like what am I going to get? Okay. The other side of that is the resolution of the object that you're going to produce. This right here has pretty much just been disassembled as sections, and then each section is basically the width of the material. So that when it's reassembled, you've essentially recreated the material in 3 dimensions. Okay, that's a decision. That's a lot of material, but it's a complete solid object, right? There's other things you can do. We'll sort of talk about that. You can get an incredible amount of resolution just with this technique. Right? You can produce some pretty like complex forms, and they've even done stuff at full scale with this technique. Okay? This scales up to architecture pretty readily. And for each one of these methods today, I'm going to show you at least one piece of architecture that uses this method at full scale. So this isn't just like for your little like desk art. This is something that's actually buildable in the real world. And of course, with the scaleless landscape of the computer, once you've got a tool that you've created for this, it's very easy to scale it up. When you do your script for me for the final project, that's what you're doing. You're creating a tool for yourself. Just as all the icons you have in your computer or on your desktop, once you've made something, some form of automation, it's reusable. If it's a good tool, it's reusable. Okay? Remember Alton Brown, we don't want any unitaskers. We don't want anything that just does the one thing and you throw it away. It's not worth making if you're only going to use it one time. Okay? It's really handy to have like a stable of these things. So another example, you can have a project, and depending upon the way that you use space in the project, right? So you can create a screen. This is a vertical example. This is from Ball State. Also, the way that you connect it together. I mean, in this case, right, you're going to laminate it with glue or some other toxic material. Here, you can see up at the top, it's basically run through these dowels or poles, right, that are mounted in the ceiling. Okay, so as a part of your sectioning process, you could accommodate a dowel or some other piece of like material and use that to create the spacing in your object. Okay, so that's something that you can design into it as part of your section. And the process would look something like this basically. The tool that you're going to create is going to output a cut sheet with the dowel holes cut into it. You can't really see here, but another important thing are the labels that are on each of these things. It's very important to keep track of like which one's which. You're going to have a digital model that's actually going to have labels in it that correspond to that. So you'll use the model essentially as your plan. I've been promised by Autodesk that there's going to be a day, someday soon, when we're not using two-dimensional plans anymore, where like everything is done by model. Okay, this is an example of that. There are a lot of projects that are done that way. Like essentially, you just open up Rhino and that's your plan. Okay, you just follow these things. This project is interesting in the fact that it actually makes thorough use of the sheet. That's the entire 4x8 sheet, and the way that it's fabricated is to absolutely waste no material. You probably got a few of these little discs to play with or whatever when you're done. I'm not sure what they did with those, but that's actually a design constraint of this project. Okay, and that's kind of interesting that they got this really kind of sinuous form without that waste. It's really nice. And this is what it actually looks like. And again, this is what you're going to undertake. So as you finish Studio into December, and it's the project's due on the 12th, and it's December 10th, and you decide to start working on it, this is what you have in front of you after you get the script done. You're going to have a pile of materials that you have to assemble. So bear this in mind. There's still the assembly process of this model, like even after you've gone through the computational methods, part. But you've got to, if you keep yourself organized, you've got 2 or 3 people working with you, like this can go pretty fast. But this is still the labor-intensive part of this method. So that's what you end up with. Some version of extreme sectioning. This is not a rendering, and it looks like some movie set or something like that, but this is actually a real project. This is a millimeter thick, basically like chipboard that was cut into sections and meticulously reassembled as these columns. The artist in question, it's an artist, I believe, not an architect, wrote some algorithm to make the forms, and then went through a process of basically sectioning these things to a very fine like precision. When they're reassembled, there are these really intricate articulations on these columns. I mean, it's kind of amazing. Like, I mean, I think it's totally amazing. That's what it looks like. So it even has like a little bit of like a texture, to it almost, right? What else do you notice about it too? I mean, when you got like thousands of these things, they don't all come out like great. In fact, the artist was saying like some of the pieces don't even like actually come free of the board. Some of them are left out. When you glue them together, they're not always like precise, but the effect is like pretty darn good though. And they're huge, they're like full scale columns. So don't, disregard just the poor contour as a method of construction, because it's kind of amazing actually. I mean, in a way, this is how 3D printing works. I mean, not by subtracting material, but by adding material in small layers. And in fact, I should have led in this. This artist has another project called Digital Baroque, and it's an alcove that's been digitally like printed, and it's pretty amazing too. Like, and it's the additive version of this process. Okay, so pretty incredible stuff there. And of course, like you guys, I think in second year we talked about this project. This is Dunescape by Shop Architects. This is one of the first kind of early digital fabrication projects. I don't know if I'd really call it digitally fabricated. It was certainly enabled by digital processes, but it wasn't like it was exactly CNC. Like it was kind of like painstakingly put together with large sheets of paper that had the plans printed out on it. This is really bad, I'm sorry. But like if you get the book, each one of the colors is like a different like layer of that thing, and they would lay down the 2x4s and they would cut them and they'd fit them to the sheets and they'd connect them, and then they built this whole monstrosity. It kind of is a beast. But it's this very idea that they had this digital form that they manipulated into the computer. It's a combination of the floor and the wall and the ceiling being all one surface. The interesting part about it was this kind of A-B thing where they basically sandwiched these things together in order to create this. So that's why they needed the different colors in the sheet. And that's how it gets its structure. It's very simply assembled. Okay, but it's still an idea of this sectioning logic, but just applied to kind of like a scissoring like methodology. So this is a very very nascent piece of shops architecture. Where they are now, but still kind of an important piece in the evolution of the idea of digital fabrication. 2001, 2000. Okay. I don't know. Some of you guys were in grade school. I don't know. that was time for me. But the effect is pretty interesting, though. You can make a space out of this too, right? So not just a screen, but a surface. So think about your model too. Like I told you guys, you can cut a piece of your form. Doesn't have to be a solid. You can take a piece of it, scale it up, and kind of make a tunnel out of it. You can kind of spatialize that form if you like. Okay. Some other examples of these. You could do radial sections. These are sound recordings that this artist did, and these are the waveforms of the sound. So it's not exactly what you guys are doing, but if you can take a section from a vector, you can also take a section as a revolve operation, and that's going to give you a completely different form. You need very small pieces to do this, though. I don't think, because the larger the material, right, the bigger the radius is going to be. It's going to be chunky. Just another example. Other materials, plexiglass, styrene, going to get you different kinds of effects. This particular piece, this is another audio piece. This is from another lecture that I did on data, but it's still relevant. This one actually fits like a slide in a tray, so there's actually a digitally fabricated tray that these fit into. Like scientific slides, like Dexter. You guys watch Dexter? So this is like the slides in the slide box. Okay? So think about how you're going to actually assemble these things. Again, glue is like kind of the lowest common denominator, right? We're architects. What kind of joinery are you going to use when you put these things together? Okay? Another example. Here's one too, and this is going to play up on the next type I talked about, the waffle. This has a finger joint, so there's a big bar that's got a piece cut out of it, and then this just slides into it. So it's kind of a variation of that last one, only both materials are translucent. And this actually gives it a bit of like dimensionality, whereas the other one, it's kind of a low thing that it fits into. This one's actually wood, and this one's like plexi. It's pretty cool. You can also, some of the scissoring things too. You could think about, taking one slice of contours in one direction, and then striking some kind of an axis, and then taking contours in the other direction, and then removing every other one and putting them together. You can even take two forms and like unzip them and put them back together. I don't know. There's lots of possibilities for you guys for these projects. All the way from the very first thing, just laminating it, which could be nice at a high resolution, right? To spacing it, extreme lamination. So there's a lot of potential for the contour. Next topology I want to talk about is the waffle. And I don't know if this is the exact nomenclature for it, but it's certainly what you're going to find a lot under. Waffling is basically like two-dimensional contouring. And the advantage of it, well, there's a couple advantages of it. The advantage of it is that it creates volume with less material. You can define volumes, differently. Even a low-resolution waffle can sometimes describe a higher resolution final form because it works across both axes. It's very stable. You get a play between the kind of space that's within it and the overall volume that you've achieved. So it's kind of a nice idea. This is something that we see, in architecture, just in a general, and just sort of a trabeated system, right? Of beams crossing each other. It's a real method of construction. It's also nice because you don't necessarily have to glue it. It can sometimes fit together just by friction alone, if you take into account the materiality of it. So it might be a little bit less labor intensive in assembly than the other methods. Okay, I don't have to have a clamp with a bunch of glue on it that I'm continuously like applying pressure to. These things might just stand up on their own. The flip side of it is that the computational aspect of it is a bit more complicated because now you're taking two sets of sections. You've got to cut each section specifically with finger joints so that these two join together the right way. Okay, and you've got to label the heck out of it because now you've got pieces that look like pieces that are going in both directions, right? So there's a few challenges, but nothing insurmountable. There's a real precedent for this, though, right, in architecture. This is Corbusier's Chapel at Ronchamp. Believe it or not, the roof system is actually a waffle. It's not actually solid. Like it's actually hollow on the inside. It's a lot less concrete in a hollow thing, and it's not going to crush the parishioners, right? It's a waffle system. It's a series of waffle vaults. I mean, vaults are like a common architectural entity too. So it's actually sections taken in the X and the Y. This is Greg Lynn, another precedent. So Greg Lynn, I don't think I've talked about him too much, but I like to think of Greg Lynn as the Jackson Pollock of digital architecture, like in the sense, and this is not meant to be insulting, but where you look at Jackson Pollock and you're like, okay, he's the guy who threw paint on a canvas. He's the guy who had the first idea. So anybody else who does it after him is like just making up Jackson Pollock, But Jackson Pollock's a pretty good artist. Like not everybody can throw paint on canvas the way he does. Greg Lynn is, in a lot of ways, for some of these early digital tropes, the first recognized or at least famous person to do some of these things. And Greg Lynn is one of the first people to use metal balls and waffling in architectural context. So he gets credit. He's first to the line. This is a gallery exhibition of his work. Each of these blobs represents a program area, and then they kind of fuse together. And I'm missing the slide, but the effect of it is that if you subtract these from the gallery space, so this is the space that he wants you to have to admire his great work. If you subtract these from the gallery outline, you're left with this form, and then he basically waffles it. Okay. Then he builds it at full scale. So there's a few fuzzy pictures of this exhibition. This is circa 1994 or 1993. So this is still pretty high tech back then. And he's doing this by hand too. I mean, he's taking the sections, he has to orient them flat, he has to lay them out in his CAD program, he has to label them manually. He's not applying computation the way you guys are, but he's first to the gate with this idea of waffling. This is kind of an idea. This isn't the same project, but it's very, very, very close to it. It's the same architect though. So scaled up. So again, the idea of waffling is that you have some form that you've created, you take sections of it, and if you can see, these are cut in the top chord, and these are cut in the bottom, and when you lay the top ones into the bottom ones, they fit together, they get you your waffle, and it just looks, you don't really see that, you don't really see those as joints, they kind of disappear into each other, okay? Notice the labeling, the Y strut, X strut, so you can see that this person really, has already introduced that. This is a nice kind of plan for yourself too, to see what's what. And the process of assembly, might look something like this. So if it's not clear, so you have ones that are cut in the top chord, ones that are cut in the bottom chord. You can cut them on any axis, depending upon your form. You might cut them in the X, one way and the X the other way, so they fit together this way. Okay, doesn't have to be this way. I'll say this right now, you're going to see some scripts online for waffling. They are not your scripts. You need to build yours, and I'm going to give you prompts to do that. It'll be pretty obvious to me if you've stolen one of them because the way they work is not the way that our script will work. So if you find these, don't go digging for that. The goal of it is to understand how to write one yourself that works the way you want to work, not to just go download one. You can go download one on your own time. Anyway, just as a warning, if you're looking for help with the waffle script and you Google a waffle script, avoid that stuff. Okay. Same with any of the other ones here. These aren't new methods. I think it's pretty clear about that. But the goal is not to plagiarize these things. See, these have the labels are laser cut, onto the form itself. So that's kind of nice. I think the person signed it too. It's nice. Full scale piece, a little bit more recent, 2010. Again, making this as kind of a vaulted structure. This is a waffle, just a really, really big waffled piece cut out of plywood. They also do things like where they're sort of fastening smaller sheets together to make larger, like unitary sheets. It's a school project. Very, very large project in Madrid. You know this one, Ginny? Yeah. Have you seen this?
Yeah.
You were there? Is it impressive? Mm-hmm. So this is it's waffled. I mean, you can see the keys here, although they employed steel for safety reasons, probably. But it's a full scale, piece. Here it is being assembled. If you have any, qualms about this stuff being useful, I mean, here it is. I think it's pretty neat. But again, your choice in like what form you create and where to make those axes like has an effect on the final outcome. Maybe you cut your waffles at a 45 degree instead of a pure X or a pure Y. Okay. More advanced version of waffling. If you get there, I mean, just having these kinds of I don't expect you to do this, but having pieces that still have these finger joints, but basically moving in the X and the Y at the same time. So you can kind of imagine there's a waffle kind of rib kind of going in this direction, and then the flat piece is the other direction, as opposed to them both being like vertical. So there's a horizontal and a vertical piece that are being waffled together. Again, pretty advanced, and this thing is like pretty much self-structuring. Again, still more advanced, waffling. There's no reason why the things have to be on axes with each other. They can just intersect each other and have finger joints. All right, this is varsity level digifab. And color. They're pretty impressive, though. Used as a screen. Fabricated out of plastic. Okay, the last one I want to talk about is what I call faceting or like polygonal. And this is essentially constructing the outer surface of your object. So whereas the other projects were about contouring, this is actually about the outside of the object, and it's basically hollow on the inside. Okay. So the other ones are about the inside and not the skin. This is the opposite. So this actually falls into another kind of classification. And this is the most complex. So you get things like this wolf made out of mirrors. But the amount of detail that I think you guys can produce in this unit for this project, I think this is what we're talking about. Like, not like too complicated. I really want to stress that. And actually, I mean, I would do it. I said something like 100 is the limit or whatever. I would do it as few as possible that like gets the point across that you want. Okay, because it is a very labor-intensive process. You could even get down to 50, and it might be fine. I think it's actually surprising how much our brains can process about a form with as few pieces as possible. The idea of this is that each of these triangles represents a plane, and this is the simplest thing you can represent in computational geometry is a plane, right? Any 3 points that are coincident, that are in the same plane, make a plane. Okay? Things that you think are squares in computers are just 2 triangular planes, basically. Okay? Everything that you're taking a facet of has to be planar, and there are like commands and tools that will make that possible. If there's a problem with your script, it's probably because you failed to take into account the planarity of like something. This is all about these triangles. Okay, that's really what we're after. And what you're going to get is something like this, and this is like exactly what we're talking about. So this is just a simple kind of double curvature form. Every single piece of that form is different, and it fits together like specifically at a specific angle to recreate that form. That's what we're talking about. This is where a lot of stuff is going right now. There are a lot of the people like Mark Forens, Skylar Tibbetts, that are doing these installations. Like they're doing like souped up versions of this, but this is where it all begins. And the method that I'm recommending, there's all kinds of ways to fasten these things together, and I think you've seen some stuff even in our own school with tabs that are folded or with like bolts. I'm still kind of interested in the friction joint because it's about fabricating all the flat pieces that let you assemble this together. Okay. This is what I'm really talking about, though, something very close to this, where you've got these like pieces that fit between 2 facets, and they have an angle cut into them, so that the facets slot into it, and that maintains the angle. Okay, and I'm going to give you guys like basically pseudocode for how to do this, so don't worry, don't freak out if you don't know how to do it. I don't expect you to know how to do it, but I expect you to solve the problems that I give you, and that will give you this script when you're done. Okay? But this is what you're going to end up with. And there's even kind of an aesthetic to it, you know, the kind of like spikiness or the kind of three-dimensionality of having these little like keys, these little shims that stick out. You can fab these out of plywood and fab these out of plexiglass, and they disappear, so to speak. Right? Materiality, or you do the opposite, fabricate the outside out of glass and the little pieces out of something solid. Whatever trips your trigger. That's a Midwestern thing too. You know, like I said, there's other methods. Which are I don't think you should do, but if you make it out of something foldable, there are lots of utilities that you can get that will actually cut tabs into it. Then what we do is we score these and fold them, and then we attach them together. This is kind of how, like, I don't know if you guys, some of you were around for this. 2 years ago, Comp Practice did a thing like in the pavilion. They did a thing out like in the salon with like binder clips. This is the technique they used. It's extremely labor intensive though to have to actually score, cut, fold these, and then attach them all together. And it's hard to maintain angles when this thing is like floppy. Okay, so that's why I really want to go with this piece right here. Okay. Other methods. This is a similar thing to the last one, only the tabs are specifically like cast or folded at an angle, and then they're kind of bolted together. So that's one method. Another method that has been used, it's becoming more vogue now, is sort of folding. So it's about taking an object and essentially computationally unfolding that material so that when you cut it, some of these lines are scores and some of these lines are cuts, and you could like fold it back together again. Okay? It's actually a difficult computational problem because folding has to conserve the material even when the angle like changes. And if you move something on the computer, it almost distorts it. And doing it without distorting it is really hard. In some forms, and you have to figure out computationally, where do I have to like stop this piece so that I have another piece that won't join the fold, right? Because it's impossible. It's not like an orange where you could peel the whole thing and the whole thing would come out as one piece. Okay? It's like a pineapple or something, right? Good luck. Okay? Some of it's going to stick together, some of it's not going to. So you have to figuring that problem out. There's a program called Pepakura. I think some of you guys, like I talked about this last year. There are programs that do this. Japanese Papercraft, right, is one of these things that kind of calls for it. You can upload a video game character into this program, and it'll create a Papercraft like pattern for you. You can make a building out of that. We're not going to do this, but I just want to tell you, as a faceting technique, folding is really useful. Something you could do, if this isn't hard enough for you, and it may not be, is you could cut a pattern, into it, so that when you do fabricate it, it has like a texture to it. You could burn an image into it, or you could use an attractor, to maybe draw some like transparency or some translucency into the material. Totally cool. It's free, right? You're just removing material. Not that hard. Okay, last, I want to talk about assembly. I think we're still it falls under the rubric of fabrication because we think of fabrication as the entire kind of life cycle of the assembly of the object. It's really, we have shown you a lot of techniques for how to basically translate something from a three-dimensional object to a bunch of two-dimensional objects for assembly. But the missing leg is actually putting the damn thing together. And in a lot of cases, there's a ton of labor involved, and it's really difficult to coordinate, and it's one of the bottlenecks of this whole thing. What a lot of architectural scientists, researchers have been working on is robotic fabrication. So having a robot take the pieces and put them together. And I think I've talked to you guys about this. You've heard this maybe 3 or 4 times now about Gramazio and Kohler's digitally fabricated brick walls. They didn't make the bricks. Like, the magic is in the assembly of the bricks, and it's done by robots. Okay, Gramazio and Kohler at ETH and Zurich are really at the forefront of these methods. So I'm going to show you a couple of videos here, hoping that my internet works. Actually, that might be a problem. Wow, and this is like, okay, okay, thanks, Vimeo. Fantastic. There's probably no sound. It wouldn't matter anyway if there was. Just take a look at this. I'll kind of narrate it as it goes. So this is what I'm talking about with this brick. There's this basically these robots that can pull bricks from piles and they can assemble them. Now, what's on their screen there? Rhino? And you'll see Grasshopper scripts in these things too. These are controlled by Grasshopper scripts. Why aren't we doing this? Why won't Chris Jarrett buy me a robot? I don't know, right? But look at these. They have little ones. They have little ones. You imagine having that on your desk? Robot, go make me my model. I'm going to get a sandwich. Now, what's amazing about this too, there's no compound. There's no joint material. Like you can make a step so that dips it in glue and then assembles it, and that would be just it's simple to code. This is just gravity. When it's a good thing too, because it really shouldn't rely on glue to stand up, right? I mean, it should pretty much be gravity. Yeah. Gotta have fun sometime. Look at this, and then, just to prove a point, right? That's all it is, just little dolls. Now the full scale is the Big Daddy, or Big Mama, whatever, gender neutral, that actually assembles these things at full scale, and it's actually portable. It fits in the back of a tractor trailer. Okay. So in the future, right, you'll have a robot that squirts out the bricks and assembles it on site, right? But you will program it, hopefully. Okay. That's a lot of fun. Third years, actually no, most of you guys, right, have been using the hot wire cutter, right? There's an app for that. The thing about robots that's interesting too is that this is the same robot, by the way. It's just like a generic industrial robot. Oh wow, we got some Moby here. Okay, we'll turn that down. You can actually fit the robot with different tool heads, right? And so this one is actually one that they designed in-house that's a wire cutting head. And so they can actually cut the shapes out of the foam and they can assemble it at the same time. Now it's funny because there's actually a step that requires a person. I think here they're actually reshaping something. Part of it too is that you can train the robot to cut the foam by basically cutting foam and having it watch you. It's pretty cool though. Trying to fast forward. So here's their Grasshopper environment that they're playing with. Yeah, it looks familiar. And so they can simulate what the robot's doing so that they know to get out of the way of it when it's doing it. You don't want to cut you with hot wire. I'll keep going here. Yeah, so then once it actually, this is the wire bed here, and once it cuts it, I think this is the part I'm looking for. I think this part's kind of funny here. Now it's pretty slow. Look at them in the background, in kind of fast motion here. Oh shoot. Yeah. So here's what the guy does. There. I'll take that off for you. And then it puts it into place in the piece. So the human's there to take the piece out. And the rest of it's the robot. Okay. So let's see if we can get a final look at some of these things. So they have like vaulting structures. So three-dimensional subtractive processes. Okay, do that one. And then last but not least, you may have seen this before. If you haven't, it's pretty shocking. So you've probably seen these quad rotor copters. Gramazio and Kohler are unsatisfied with having mechanical arms fabricating things. because they don't scale up too well and they're not that portable. So they've experimented with miniaturized robots that can assemble things out of units. So this is the space that they have set up, and this guy is actually testing the infrared system. So what there are is inside this space there are a series of infrared pieces. These are what the robots will use to see the space. These are pre-cut, like robot-cut bricks. They're being treated with an adhesive in a certain way. Again, there's no way. You could probably automate this too. And these are the helicopters, and they live on these little pedestals, and they fly down and they get their bricks. And they have like a little suction device. And then they fly into the space and they set it down. So like drones, basically. We'll keep going here. Yeah. And there's actually, and then they just go boom. Because they got to get that glue to stick, you know? Now that's kind of neat. Okay, like helicopters do that. Wait till you see 4 of them doing it at the same time and not running into each other. They have to know where they are as well as where the structure is. And they have to know what the state of the structure is too, right? So that they know where to place their payload. Okay. And this takes a long time. Like they're speeding this up quite a bit. But this is the software that they use. So this is a graphical representation, you know, in the computer, in their brains of like what's happening. This is the sort of like data that they have. So they're actually tracing their flight paths and checking with each other to make sure they don't crash into each other. Let me see if I can get. And there's people like in the space, you know, supposedly not being mauled by flying bricks. Yeah. So anyway, let's keep going. See, there's one here. There's one there. It's pretty cool. I guess they didn't get all 4 of them going at the same time, but they could. Anyway, so your like robotic overlords are like waiting for you. Question. To assemble? Oh, like a day. Yeah, it wasn't like it's pretty slow. Yeah. But you know, it's proof of concept. I mean, like, you know, 9 months before this, none of this stuff. They had quadcopters and they didn't have any of this stuff. It's getting faster. They're actually experimenting with like smaller, even smaller ones too. That work in squadrons and things. Like it's pretty scary. Yeah. I don't have a link to it right now because it's a bit embedded in the talk, but you should look at Skylar Tibbets' TED Talk on self-assembly. The other notion is that you can print things out of multiple materials, and then when you subject them to electricity or water, they essentially fold into the structure. So if you want a sphere, you don't fabricate all the little pieces of the sphere. It basically makes a loop, like a big loop, and then when the charge is applied, it folds back up into a sphere. So it prints flat and it becomes structural. It's pretty scary stuff. Okay, anyway. What you guys are going to do, you know, is the front part of this, which is essentially this translation from a 3-dimensional object to a 2-dimensional object. So have a look at the slides, look at some of the precedents that I'm going to link to, decide with your partner on your strategy that you're going to take. It's okay to do a couple of contours now, just to see what that might look like with the resolution of the form that you're trying. Okay? Nothing's going to stop you from doing that. JP and I are going to review your work on Monday and Wednesday, and we'll give you some advice on like whether it's going to work or if it needs to be simpler, you know, that sort of thing. What we're aiming for is something we can fabricate here in the laser. It's going to be roughly, 12 inches by 12 inches, you know, cubed. It could be a little bit bigger, 12 by 12 by 18. Okay? It's just something that you can afford to do in terms of time and in terms of material. But take into account the craft of these things. Like I don't want to see a bunch of really badly burned like cardboard, you know, things. Like I think like things like museum board and acetate and plexi. You know, think about this as a nice like artifact, something for your portfolio. A lot of you guys are headed towards like graduate school or towards professional practice. It would be good to like demonstrate, you know, beyond, because sometimes in your own project you're not able to do really, really funky stuff. So maybe this is an opportunity to kind of show off. So take it as that. You've got plenty of time to do it. You've got at least, you know, 3.5, 4 weeks before the end of the term. So, you know, think about it. Let Jake or I know if you guys have questions about it. That's it. I'll see you guys later.